In today's video, we're going to be talking about inclined planes. After you're watching this video, you should A, know what an inclined plane is, and then B, be able to determine the net force and acceleration of an object on an inclined plane. So let's get right on to it. What the heck is an inclined plane? Well, basically, an inclined plane is a surface that's tilted rather relative to like a horizontal surface. And so typically if you put an object on a tilted surface, it starts to slide down the object. And this probably is just common sense, but I'll say it anyway. The more tilted a surface is, the faster the object slides. So let's say you have an inclined plane that looks like this, and you put a box on it. This one will move or slide slower this direction down the plane compared to, say, an inclined plane that looks like this. Okay, this one would go faster. Okay, so just kind of conceptually knowing that is useful for solving problems, just having that in the back of your mind. With an inclined plane, there are always at least two forces acting upon an object that is positioned on the inclined plane. Okay, and it's just like drawing free body diagrams. There's always the force of gravity. As long as we're on Earth, there's going to be the force of gravity, and then there's going to be the normal force. Now that's the very basics. Now there always could be an applied force that someone's pushing the box or pulling the box or whatever the case may be. Also there is the force of friction that could get involved. So it just depends on how complex the problem is, but at the bare minimum, there's always going to be at least two forces acting on the object. Keep in mind, the force of gravity always acts directly down. Gravity doesn't care if you're on an inclined plane or not. It always acts directly down. Whereas the normal force acts perpendicular to the surface. So on inclined plane problems, it's not going to always be straight up. It's going to be kind of angled in a way because it's on an inclined plane. Okay, so a little bit of changes here in terms of what we've been used to in previous lessons. So here is an example of a picture anyway. For inclined plane problems, I highly recommend resolving the force of gravity into x and y components. Okay, you'll notice here's this inclined plane that's kind of like half drawn in, but I'll just finish it. Okay, there's a box on it, and the force of gravity acts directly down. I highly recommend kind of setting up your axes, if you will. Like here's your y-axis, and here's your x-axis. Okay, so x and y, like this, in line with the plane itself. So the x-axis is parallel with the plane, the y-axis is directly perpendicular with the plane. So you'll notice the force of gravity doesn't really fall on the x or y-axis, so you have to break it into components using trig. The reason why I pick gravity as the kind of oddball to kind of, not follow the x and y axes is because then it makes these problems a lot easier, because typically there's going to be an applied force along the x-axis, the force of friction acts along the x-axis, and the normal force acts along the y-axis. So basically what I'm doing is I'm just making it that there's only one force that you have to resolve into the components of x and y, and the other ones, they're just done for you already because the problem usually gives them to you in that regard. Okay, so I highly recommend resolving the force of gravity into x and y components. And I'll show you how you do that in just a second, but I just want you to kind of keep that in mind. So in this picture here, basically they've taken this force of gravity and they've resolved it into components. You have a force of gravity perpendicular to the plane, and the force of gravity parallel with the plane. And this parallel piece is actually what causes the box to accelerate down the plane in the first place. Okay, if the force of gravity was just acting straight down, things don't move, right? I mean, like that's why like your cup of milk sitting on a table doesn't just start sliding off the table due to the force of gravity. But if you tilt that table, now the force of gravity is able to act on it and cause it to move. So for a practice problem, I want to kind of practice resolving gravity into its components. A couple little like geometry things I just would like you guys to note. You may know this already, but a triangle, if you add up all three angles, a triangle's angles add up to 180 degrees. Okay, so keep that in mind. A triangle's angles add up to 180 degrees. The second thing is that a right triangle has one angle that 90 degrees. Okay, so a little bit of geometry review for you. It may be said better in geometry class. I personally haven't had taken geometry in a long, long time, but just a refresher on two things that come into play when we're dealing with inclined plane problems. All right, so I'm going to draw a relatively large inclined plane here just because it makes things easier. Oh, I wish I could draw straight lines nicely. Anywho, this angle right here typically is given to you in a problem, and I'm going to say it's 20 degrees, okay? I'm going to put a box on this inclined plane, okay? And as I said before, I recommend resolving the force of gravity into its components. Now, the force of gravity is going to act directly down, okay? The force of gravity is going to act straight down, F sub g, there she be. Then there can be all sorts of other forces acting on this box, like the force of friction would oppose the motion of this box sliding down the plane. I'm assuming it's sliding down to the left. You have the normal force that's acting perpendicular to it. And heck, let's say someone's pulling on this box. We can even put an applied force here to make it like slide down the plane quicker. All right. So you'll notice those three forces there, they all are in line with the x and y axes. So there's no reason that you have to break that force into components. The force of gravity, though, is not in line with the x or y axis because we kind of have tilted our axes, if you will. And so we need to break it into components. Now, how do you do that? That's what I want to show you guys in this slide right here. I'm going to use yellow, and basically my y-axis is going to drop down just like so. Okay, that's my y-axis. And I'll call this F, G, Y. And my x-axis I will make in, oh, let's use green. The x-axis I'll make in green. Okay, and we'll call that FGX. Okay? Now, here's the thing. How did I know where to draw those dotted lines? The FY, or FG sub Y, is going to be perpendicular to the plane of the inclined plane. Okay, so it basically just, it's in line with the normal force. Okay, so you just draw a dashed line going straight down from the normal force. Fg sub x is going to be parallel with the plane of the inclined plane. Okay, so you'll notice this green line is parallel with this plane here, and this yellow line is perpendicular to the plane. All right, to resolve the force of gravity into components, I need to know this angle right there. Okay, and how do I figure that out? Well, that is kind of the question. And this is where you're going to have to use some geometry. Let me get a color I haven't used yet. This right here, this angle is a right angle, right? That we just solved that, okay? That's a right angle there. Or we just didn't solve it, but we just kind of drew it to make it a right angle. The best way I've found to figure out this angle here, the in green, is to basically extend your force of gravity line all the way down to the base of the plane, or the inclined plane. And I've made another right angle here. Okay, that right angle is 90 degrees, right? So if I know this right angle here is 90 degrees and this one is 20, what must this angle right there be? This little guy right there, what must that angle be? Well, I just take 90 plus 20, that equals 110, right? And I know that a triangle's angles must add up to 180 degrees. So 180 minus 110 is 70. This angle there must be 70 degrees. Now that's not the angle I'm interested in, right? That's not really what I care about. But here's the trick, and hopefully this is making some sense. This dashed yellow line right here and this red line of the plane make a right angle. It looks kind of like this. Okay, this is a right angle here. Okay, so in total, this is 90 degrees. Okay, from this red line to this dashed yellow line, that is 90 degrees. Okay, 90 degrees right there. I know that this part of the purple is 70. So what must the green piece be right here? Well, if I just take 90 minus 70, and let me get a color that's actually visible. Blue is not so good. 90 minus 70 is 20 degrees. And so this little tiny angle here must be 20 degrees. Right? And now we've got it. Okay? And this goes much faster once you start to get it. It's just I'm trying my best to explain it so that hopefully everyone can catch this. Because without that angle, you're not able to solve for f sub gy or f sub gx. And we'll do a practice problem with this in just a second. because we can't actually solve for it because I didn't give you what the weight of the mass of this box is, and so we can't calculate the actual weight, and we can't do any of these other things. This was just to show you how to get that angle. Okay, so 20 degrees would be the angle. Let's move on. This formula can be useful, or at least you may find it useful. Works only if friction and other forces are not present. So basically the only force acting on this object would be the force of gravity. So let's say I put a box on an inclined plane, and I tell you the mass of it. You can use this formula to figure out the acceleration of the box. The thing is you need to basically figure out that angle that we just talked about in the triangle. Okay, so the acceleration of that box, if there's no force of friction, no one pushing on it, pulling on it, or anything like that, you just take 9.8 times the sine of that angle that we just talked about in the previous slide, and that will give you the acceleration of the object, okay? Because the only force acting on it is the force of gravity. Okay. If there's other forces, which the next example I'm going to do, are acting upon it, this formula is a no-go. Okay. So here's an example problem of something that I could ask you. All right. It says a 100-kilogram crate is sliding down an inclined plane. The inclined plane is at an angle of 30 degrees. The coefficient of friction between the crate and the incline is 0.3. Determine the net force and the acceleration of. So I would love to have used that formula that I just talked about in the previous slide. The problem is that there's another force other than gravity acting on this this box, and that's the force of friction. Okay, and that's going to cause issues in terms of how fast this box accelerates down this plane. So basically, we're going back to what we've been doing all along. We're going to be calculating the net force. We're going to be breaking the force of gravity into components. And then with the net force, we're going to be able to calculate the acceleration. I'm going to switch to a different slide. Basically, I kind of cut a lot of the gobbledygook out of there and just gave us the important information. The mass of this box is 100 kilograms. The coefficient of friction is 0.3. Okay, so what is the acceleration of this box down this inclined plane? Okay, the first thing I want to do is I want to calculate the force of gravity, right? And the force of gravity is simply mass times gravity. The mass is 100 kilograms. The gravity is on Earth anyway, is 9.8. So 100 times 9.8 is 980 newtons. Okay, that is this piece right here. That is like the hypotenuse of this triangle. Okay, notice this is a right triangle, right? This is a right triangle right there. Okay, I need to know what this angle is right here. Okay, what is that angle? Well, they have very nicely given us the components of the force of gravity. So this is force of gravity in the y direction, and this is force of gravity in the x direction. Okay, so I need to figure those out. What does that equal? Okay, so to do that, I'm going to actually extend this line straight across. And you can do this too. If the problem doesn't give you the whole plane, you can just make it, you know, and then everything's good. Now, I just made a right angle with this line here and with the force of gravity, right? This is a right angle. So this is 90 degrees, okay? This is 30 degrees. This angle here is 30 degrees. So I'm going to say, well, 90 plus 30 is 120 degrees, right? Remember, all triangles must add up to 180 degrees. So what must this angle be right there? Okay, what must that angle be right there? Well, if I take 180 minus 120, I get 60 degrees, right? So this angle here must be 60 degrees. But sadly, that is not the angle I want. I want that angle right there. Well, if you remember, I said this here is actually a right angle, right? In total, it makes a whole thing of 90 degrees. So 90 minus 60 is 30. And so that angle right there is actually 30 degrees, okay? Why do I care so much about that? Well, that angle is what's going to open the door basically to allow me to use trig functions to figure out f sub gx and f sub gy. Okay, so let's do that. Let me change pen colors for that. So I'll do f sub gy first, okay? Basically, I need to know cosine of 30 degrees, because we need to just calculate that, equals f sub gy over the hypotenuse, which is 980 newtons. Okay? And if I do that math, I get an f sub gy that equals about 849 newtons. Okay, so I did a little bit of rounding, but basically you just do that math right there. To get f sub gx, I'm going to take the sine of 30 degrees equals f sub gx over 980 newtons. And if you do that math problem, I get 490 newtons. Okay, nice. Okay, so why do I care about that? Well, basically, f sub gy, there is 849 newtons of force pushing directly down or perpendicular to the inclined plane. So who's going to balance that 849 newtons in the y direction? Well, that is the normal force, right? The normal force. And so I now know what the normal force is, right? I know the normal force is 849 newtons, okay? What is the force of friction? How can I figure out the force of friction? Well, the force of friction is going to be a formula that we had talked about a while back. Let me get a color that works well with black. Force of friction equals mu times the normal force, okay? Which we know mu, which is the coefficient of friction, is 0.3. We know the normal force. We just calculated it, right? It's right here, 849 newtons. So if you do that math problem, I get a normal force of 255 newtons, okay? So the force of friction, this thing that's going to oppose the motion of this box sliding down this inclined plane, is 255 newtons, okay? Is there any other force in the x direction besides the force of friction? The answer is yes, there is. It's the force of gravity in the x direction, right? And that's 490 newtons. Okay, so before I talk about that, let's just kind of take a look and see what are my forces in the y direction and what are my forces in the x direction. Well, in the y direction, I have a normal force of positive 849 newtons, and I have a force of gravity that would be negative 849 newtons. And sorry, this number actually should be negative. This number should be positive. I was labeling the wrong things. So that all adds up to 0. Okay, there's no net force in the y direction. How about the x direction? Well, the force of friction I'll call positive because it's going to the right. So it's positive 255 newtons. And now, is there any other force in the x direction? There is. It's this 490 newtons, which I'm going to call negative because it's moving to the left. Negative 490 newtons. If you take the difference between those two numbers, I get a net force of 235 newtons. Okay, so I'm going to call it F net equals 235 newtons. After all of that, and you may be saying, where is this going, man? We talked about this thing called Newton's second law. And Newton's second law basically says F net equals mass times acceleration. Okay, so we can finally calculate the acceleration, which is what this problem was originally asking for. So the F net is 235, wish I could write better, 235 newtons equals mass, which they give to us, it's 100 kilograms, times the acceleration, which is what we're looking for. And if you do that math problem, you get an acceleration of 2.35 meters per second squared. All right. That's one example of an inclined plane problem. I really can't change it up all that much more. I could add an applied force to it, but basically if you can get the basics of this, you'll be sitting pretty. That takes care of this video. I will see you guys next time.